Okay, so let's do some other examples of benzene and spectroscopy. So we'll take a look at 15.41, letter A, deals with the chemical formula of C10H14. In the IR spectrum, we have a peak of significance given at 745 inverse centimeters. That's going to help us with the substitution in this example because there's not a lot of other information that's given. In the proton NMR, we have a 4-hydrogen broad singlet at 7.18 parts per million. We have a 4-hydrogen quartet at 2.70 parts per million. And we have a 6-hydrogen triplet at 1.20 parts per million. So first thing we want to take a note is let's start with the 4-hydrogen broad singlet at 7.18 parts per million. Now, these have to speak to the hydrogens. So this peak has to speak to the hydrogens on the benzene ring. Because remember, between 6.5 to 8.5 parts per million, the only type of hydrogen that can rise to a peak or peaks in that range are hydrogens on something aromatic, like a benzene ring. And because there's 4 hydrogens in this area, what it speaks to is the fact that the benzene ring is di-substituted, okay? 5 hydrogens in that area would speak to mono-substituted, 4 would speak to di-substituted, 3 would even speak to tri-substituted. But we know for di-substituted, there's a couple different arrangements, ortho, meta, and para. Now, here we're dealing with a broad singlet. So one of the things that sort of comes to my mind when I think of a di-substituted that could give me all 4 hydrogens as being equivalent would be para di-substituted, where both branches are the same, because then all of the ring carbons that have hydrogens left would actually all be equivalent. And therefore, all 4 hydrogens would be equivalent. And they should be represented by a singlet. However, the other piece of information that we can't ignore is the peak at around 745 inverse centimeters. If it was truly para di-substituted, you would have, in the fingerprint region, you would have a single peak in the range of 810 to about 840 inverse centimeters. We don't have that here. We have it in the range of 735 to 770, a single peak in that range, and that indicates ortho, di-substituted. So maybe the machine is again having a hard time reading the splitting of the hydrogens because maybe the peaks that would be present are so close to each other. Okay, just like we talked about with mono-substitute, where you would expect to find a doublet and 2 triplets, sometimes you find that 5-hydrogen singlet. Well, maybe that's going on here again. But we can't deny the 745. That tells us that it's ortho di-substituted. So what do we got left? We've got a 4-hydrogen quartet, a 2.70, and we've got a 6-hydrogen triplet at 1.20. So let's start with the 4 hydrogens first. In theory, 2 options, 4 equivalent CHs or 2 equivalent CH2s. Now we know because we have only 10 carbons and 6 of them have already been used with the benzene ring that it can't be 4 equivalent CHs. So the only possibility is 2 equivalent CH2s. So that takes us now from 6 carbons to 8 carbons. So there's only 2 carbons left, 6 hydrogens. Well, if we have 2 carbons left and 6 hydrogens, most likely that means that we have 2 equivalent CH3s. Can't be 6 equivalent CHs, can't be 3 equivalent CH2s, it has to be 2 equivalent CH3s. Okay? So, with this in mind, what are the possibilities? Well, in essence, there could really only be 2 possibilities. Excuse me. One of them would be to attach CH2, CH2, CH3 to the benzene ring, and then ortho to that would be to attach the CH3. The only other possibility would be to attach both CH2s to the benzene ring, ortho to each other, and then attach the CH3 to each of them. Now, hopefully you can very quickly tell which one of these can't be correct, and it's the first one that can't be correct, because if you look at the first one, the CH2s are not equivalent, and they have to be, and the CH3s are not equivalent, they have to be. But if we look here, the CH2s are equivalent, they have exactly the same connectivity, and the CH3s are equivalent, they have exactly the same connectivity. For the 4 hydrogens, for the 2 CH2s, how would we figure out their splitting? Pick one. Here's the carbon it's attached to. Here are the 2 neighboring carbons. There's no hydrogens here. There's 3 hydrogens here. 3 and 0 is 3. 3 plus 1 is 4. Quartet. For the 6 hydrogens, pick one. Here's the carbon. I'll pick this one here. Here's the carbon it's attached to. This is the only neighboring carbon. Has 2 hydrogens. 2 plus 1 is 3. Triplet. Now let's talk about the hydrogens on the ring. Because in theory, you wouldn't necessarily expect to find them all equivalent, because they're not. The top and the bottom ring carbons are equivalent. Sorry, so I meant to make that an A also. The top and bottom ring carbons are equivalent. So those 2 hydrogens are equivalent. And the upper left and the bottom left ring carbons are equivalent. So those 2 hydrogens would be equivalent. Now, for the H's labeled A, we'd have a peak for 2 hydrogens. For the splitting, pick one. I'll pick this one here. Here's the carbon it's attached to. These are the 2 neighboring carbons. 1 hydrogen, no hydrogens. 1 and 0 is 1. 1 plus 1 is 2. Doublet. Then for B, the other 2 hydrogens, I'll pick one. Pick this one here. Here's the carbon it's attached to. I'm going to visit this neighbor. I'm not going to visit this neighbor. Why? Because these hydrogens are equivalent. And remember, equivalent hydrogens don't split each other. So I only visit this neighbor, has 1 hydrogen. 1 plus 1 is 2, doublet. So what probably the case is that these peaks are so close that it almost looks like there's one continuous broad peak, and they read it as a 4 hydrogen singlet. But in essence, what you would mostly expect to find would be 2 hydrogen doublets in the 6.5 to 8.5 range.